Hello everyone. So this topic is on wide swing cascade structure, another modified current mirror structure that we are going to study. So before going to that one, we need to identify what is the requirement to have another sort of current mirror. So if you study this cascade current mirror structure one more time, then you will feel on the output side the drain voltage is equals to VDS at plus threshold voltage, and that's how we are creating the match with this M1 and M2 drain voltage. But then if you go on top of this M4 MOSFET, then you need another VDS set. So that means to run this M2 M4 branch, you need a minimum voltage of 2 VDS set plus threshold voltage. So this is the minimum required voltage to drive these two MOSFET in saturation region. On the other hand, this M1 and M3 branch requires like 2 VGS amount of voltage to run them in saturation. So that means you need like 2 times VDS at plus threshold voltage, even higher voltage requirement. So as you can see, M1 and M2, they are sharing identical drain voltage, and that's how they are making perfect current mirror. But M3 and M4, their drain voltages are not necessarily identical. So that also says that okay, how your perfect matching is coming. Your perfect matching is mainly from this lower pair. Upper pair might have some sort of mismatch. Okay. Now let's see what is really happening because this load branch of your current mirror, like say M2 and M4, is intended to drive another block in your circuit. But over here you need at least or this minimum amount of like 2 VDSR plus threshold voltage amount of voltage. So that's a large voltage requirement. And just to give you the perspective, the threshold voltage is usually say in the range of 800 to 900 millivolt for 0.5 micron process, and VDSAT is only 200 millivolt. So threshold voltage amount of voltage is actually really high for chip level design. So that is not necessarily a low voltage design. So our intended application should have like as low voltage as possible to drive this current mirror. So in ideal case, which is such supposed to be like only 2 VDS set, like what we are showing in the bottom picture. Okay, but to do that, somehow you need to create a gate voltage of 2 VDS set plus threshold voltage, right? So because if you can drive this M4 device by this 2 VDS set plus threshold voltage, then after this VGS cancellation of M4, say your gate voltage of the M4 is 2 VDS set plus threshold voltage, and then if you go down through the gate to source terminal of this M4, then you have to subtract VDS set minus threshold voltage. So that's why you will end up with like simply VDS set at the drain terminal of M2. Okay, so our target is right now, how can you create this 2 VDS set plus threshold voltage at the gate terminal of the M4? So here is the architecture. What you can do, instead of simply cascading, we connect the gate terminal of the M4 to another device, which is called the, we are defining like a MWS MOSFET, but that MOSFET dimension should be a little bit different. So both of your reference branch and that MWS branch is sharing the same current, reference current. Okay, but the dimension of this MWS MOSFET should be a little bit different. So how can you really find out these things? So if you look at this equation, what is the VGS expression for a MOSFET? Like for this MWS MOSFET, it should be simply what? VDS set plus threshold voltage. But that VDS set of this MWS should be 2 IREF over KPN times W over L MWS. Okay, so that's what you're writing over here, and that value, that VGS value, should be somehow equals to 2 VDS set plus threshold voltage. This is our target. Okay, so for which dimension or for what combination of that W over L of this MWS MOSFET will create this kind of relationship. So if you simplify the math or do simple mathematical manipulation, then you will end up with a expression like this. W over L of this MWS MOSFET should be 1/4 of W over L 4. So that means whatever that M4 MOSFET dimension, the 1/4 of that dimension should create 2 VDSat plus threshold voltage. So that's why we simply connect a diode connected MOSFET and another diode. That diode is actually controlling the top MOSFET. So if you look at this architecture, this wide swing cascode architecture, to bias these two cascode devices M2 and M4, you have actually two diode connected MOSFET, separate diode connected MOSFET. They are not sitting on the same branch. Okay, and the main benefit is that right now at the top section of M4 you will have 2 VDS set amount of voltage. That's the required voltage to drive these two devices in saturation. Okay, we have also covered this thing. Now in real case, like yeah, you can always have a minimum voltage like say A, but for device dimension mismatch or bias and so many other cases, what could happen that okay, you can lose your minimum dimension value, okay, and then that can drastically drive your device to the linear region instead of saturation region. So that's why sometimes it's always better to have a design which is almost like a C point, so that even after that mismatch or device dimension change, you can still maintain your saturation region operation. And finally, if you look at this one, so your VDS SAT value, or the drain terminal, not the VDS, drain terminal voltage of your M at the top of this M4 is simply what, 2 VDS SAT. Okay, but if you in regular case, this M1 was directly diode connected, so that means it was simply VDS SAT plus threshold voltage. So there is a mismatch, or also the mismatch between M1 drain and M2 drain. Okay, to match that component, what you can do, we can add an extra device like M3. We know that the drain of this M4, or sorry, the gate of this M4 is at 2 VDS SAT plus threshold voltage. Okay, so if somehow we can subtract that VGS amount of voltage from there, then we can create either VDS SAT at the output of the M2, and if we do the same thing on the M1 side, M1 for M1 MOSFET, that subtract a VGS value, then we can also have only VDS amount of voltage on the drain terminal of M1. Okay, so that's why what we are doing, we are simply adding a M3 device, another M3 device over here, so that after subtraction from the 2 VDS SAT plus threshold voltage, it will be simply VDS SAT at the output of this M1 MOSFET. So in this case, what will happen, both M1 and M2 will share the same VDS SAT voltage. So one more time, the drain terminal of M1 is right now simply VDS SAT, not VDS SAT plus threshold voltage. So that extra threshold voltage term is gone. So both M1 and M2, they are sharing same VDS SAT. So that's why you will have the perfect current mirror matching. But because of these two parallel branch biasing, M2 and M4, both of them will require only VDS SAT amount of voltage for saturation region operation, and that will give a minimum required voltage equals to 2 VDS SAT. Okay, so that's why it's called the wide swing. You are allowing higher swing of your signal because you have eliminated one of your threshold voltage requirement from the required supply voltage. And one more thing, if you also look at the output resistance of this device, it will also turn out to be pretty much identical to your cascode current mirror device. So either way, this wide swing cascode structure is then providing lower supply voltage requirement, but pretty much similar characteristics like a regular cascode structure. Okay, so can you think of one disadvantage of this wide swing cascode structure? It is giving you all the benefits. Yes? It is giving you higher resistance like regular cascode. It is giving you minimum voltage requirement, which cascode structure, regular cascode structure couldn't do that. But what could be the potential problem from this wide swing cascode structure? You can pause this video for a second and then think about that, what could happen. So if you really think about this, let's say what is happening for biasing this M2 and M4, you have two parallel branches, right? So those two things are like two extra current loss. So that means for wide swing cascode structure, you will have higher power consumption because of this one extra branch. Okay, so I think that's the only thing that we can see from here in a straightforward way. Okay, so wide swing cascode structure will take extra power to give you that special benefit. Okay, so I think that's all. So far we have studied these two modified current mirror structure, cascode and wide swing cascode. Maybe in your design you can choose either of these depending upon your requirement. Okay, so that's all. Thank you.